Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture, we studied force vibration analysis of multi-degree of freedom undamped systems. We studied two methods to analyze the force vibration response. One was the direct method and other was the modal analysis method. If the vibration response is also to be predicted, then the modeling of damping becomes necessary, and hence in this and the next lecture we are going to talk about modal analysis of multi-degree of freedom systems with damping included. In this particular lecture, we are going to focus our attention on modal analysis of multi-degree of freedom systems with structural damping. So, we are going to talk about modal analysis of multi-degree of freedom systems with structural damping. So, we have studied in the previous lecture single degree of freedom systems with structural damping, right. So, we have studied single degree of freedom systems with structural damping, and we saw that the structural damping is because of hysteresis effect. Right. And we saw that the time domain model or time domain analysis is difficult because there is no suitable model available for structural damping in the time domain, as no suitable model is available. However, we saw that the steady state response analysis to harmonic forces can be carried out with structural damping. Okay. But we had the steady state response to harmonic forces can be obtained using the frequency domain model. And we defined what is called as structural damping coefficient. Right, we defined a structural damping coefficient denoted by H, okay, and so the structural damping coefficient was defined at a harmonic frequency omega, and hence this corresponds to a frequency domain representation of the structural damping. And we also defined what is called as loss factor, which is given by ratio of structural damping coefficient and the stiffness. So, this is something we defined for the single degree of freedom system. We also defined for single degree of freedom system what is called as complex stiffness, and this was equal to the stiffness K plus IH. So, this was the complex stiffness. So, this complex stiffness quantified the combined resistance of elasticity and damping, right, to any displacement. Now, for a multi-degree of freedom system, if we write equations of motion, right, then we would see that the damping term is characterized by damping matrix H, right, and then the combined resistance of the elastic forces and the damping forces can be represented by a complex stiffness matrix, right. So, basically the complex stiffness in a case of a single degree of freedom system takes the shape of a complex stiffness matrix in case of a multi degree of freedom system. So, we will have a complex stiffness matrix which will be K plus I H, and the equations of motion in the frequency domain can be written as, by extending the equation we got for a single degree of freedom system, the equation can be written as minus omega square m x of omega plus complex stiffness matrix which is K plus I H times x of omega is equal to f of omega. So, x of omega is the amplitude of the steady state response at frequency omega, and f of omega is the amplitude of the harmonic forces. It is basically a harmonic force vector, amplitude of the harmonic force vector at frequency omega. So, therefore, this equation is in the frequency domain. Now, we would now like to define or rather we would like to see that what is the eigenvalue problem for a multi-degree of freedom system with structural damping. So, let us look at EVP or eigenvalue problem. Now, defining the eigenvalue problem for a system requires writing the differential equations in the time domain when no forces act on the system, because eigenvalues and eigenvectors are supposed to represent the free vibration characteristics, the natural vibration characteristics, and hence the differential equation has to be written with no forcing term. Okay. But as we saw that having differential equations for a system with structural damping is difficult in the time domain, and hence strictly speaking we cannot basically write or very rigorously define eigenvalue problem. However, with a limited objective of performing the steady state response analysis via modal analysis, okay, which is nothing but the analysis in the frequency domain, we would try to define the eigenvalue problem in the time domain by assuming that the frequency domain model, that is the represented by complex stiffness matrix, can be used in the time domain. So, that is the assumption we are making, that the damping and the damping force along with the elastic force can be represented by complex stiffness matrix, okay, to write the equations of motion. So, that is an approximation, though not very exact. So, therefore, in the time domain we can write the equations of motion as mass matrix times the acceleration vector plus the complex stiffness matrix, which is K plus H multiplied by displacement vector is equal to 0, right. So, this is nothing but the equation of motion in the time domain for free vibration. So, now let the displacement vector is given by say x naught e to the power I omega t. Let us say this is the solution, the free vibration solution. So, if we substitute this in the differential equation, what we get is minus omega square m x naught plus k plus I h x naught, right, multiplied by e to the power I omega t. Okay. So, in this equation for a arbitrary value of t, e to the power I omega t cannot be 0, and hence the only way this equation can be satisfied is when this term in the bracket is 0. So, let us write that on the next page. So, what we have is now k plus I h is equal to lambda m x naught. So, where we have represented x omega square by lambda, right, we have replaced omega square by lambda. So, this is something we are getting, and now this is in the form of a generalized eigenvalue problem, right. This is nothing but it represents eigenvalue problem. Okay. So, if we solve this eigenvalue problem, then we can find eigenvalues and eigenvectors. Now, there are two possibilities here. There are two possibilities regarding how damping is distributed, right. So, damping distribution there are two models or two basically possibilities of analyzing the effect of damping. One is what is called as proportional damping, and other is non-proportional damping. Right. So, we will consider both of them. Let us first of all take proportional damping. So, proportional damping refers to a damping distribution which is proportional to either the mass matrix or the stiffness matrix or to a linear combination of the two, right. So, if you take a distribution where the damping is proportional to a linear combination, then we can write the damping matrix H as linear combination of beta k, linear combination of stiffness and mass matrix, and therefore beta k into stiffness matrix plus beta m times the mass matrix. So, here beta k and beta m, they are proportionality factors. Okay. So, this is the proportional damping. So, now if we solve the eigenvalue problem, we would get basically solution of eigenvalue problem. It gives us eigenvalues which we can represent as say lambda r is equal to p r plus I q r. So, the eigenvalues we get, they are complex, right. So, we get eigenvalues which are complex, and hence let us represent them by lambda r equal to p r plus I q r, with r varying from 1 to n. So, assuming the system to have n degrees of freedom, there will be n number of complex eigenvalues, and we will also have corresponding eigenvectors, and let us represent the eigenvectors by psi with r varying from 1 to n. So, this is something what we get, eigenvalues and eigenvectors, n number of those quantities. Now, what is this PR and QR and psi r, these quantities, do they have any relationship with the characteristics of the corresponding undamped model? So, before we answer that, let us first look at what are the orthogonality properties. for this system. Orthogonality properties. We have derived orthogonality properties for a multitude of freedom systems without damping, undamped system, and proceeding similarly it is easy to derive the orthogonality properties. So, let us straight away state what those properties are which we get after deriving. Those properties would be, if we have the eigenvector matrix psi, then psi transpose M psi, this would be a diagonal matrix, right, with modal stiffness as MR, and now we will have K plus IH. So, that is the complex stiffness matrix, and this gives us basically a diagonal matrix KR, and we are putting an over bar over this, right, just to indicate that it is based on the complex stiffness matrix. So, that is the modal stiffness, and this also will be complex. So, now what is seen is that the eigenvectors which we got, right, that is psi eigenvector matrix, all the eigenvectors or the eigenvector matrix, it is found that these eigenvectors they are real, they are real eigenvectors. So, although the eigenvalues are complex, the eigenvectors are real, which basically means that the phase angle between any two elements of any eigenvector, that phase is either 0 degree or 180 degree. Okay, that is the meaning of a real eigenvector. So, the phase angle between any two elements of an eigenvector is either 0 degree or 180 degree. Okay. So, that basically is the test to check whether the eigenvector is real or not. So, we find that for a multitude of freedom system with proportional structural damping, the eigenvectors are real, and it is also seen that these eigenvectors, they diagonalize the stiffness matrix, which means that if I take the product psi transpose K psi, then this is found to be diagonal, right. Okay. So, and is equal to KR. So, we see that this is diagonal based on the eigenvectors found from the complex eigenvalue problem, based on the complex stiffness matrix and mass matrix. The eigenvectors obtained from there, they are found to they are found to be real, and they are also found to diagonalize the stiffness matrix of the system. So, conclusion is that the eigenvectors found, they not only diagonalize the mass matrix, but they also diagonalize the stiffness matrix, and hence these eigenvectors should be nothing but the eigenvectors of the corresponding undamped model, of the system, because then only they would be able to diagonalize both these matrices simultaneously. And hence we conclude that the eigenvectors we got for this system, they are same as the eigenvectors of the corresponding undamped model. And how do you obtain corresponding undamped model? Just simply ignore the damping matrix. The model that is left is nothing but the corresponding undamped model. So, if you solve that model, the eigenvectors found would be same as the one we just found using the mass matrix and the complex stiffness matrix. So, therefore, if we look at the damping matrix, right, then the damping matrix also would be diagonalized by these eigenvectors, right, because if I look at the damping matrix, which is H, then because the damping matrix is a is proportional, it is a linear combination of mass matrix and stiffness matrix, it would basically diagonalize the damping matrix also, and let us represent that matrix by HR. Okay. So therefore, if we look at the orthogonality with respect to the complex stiffness matrix, which is K plus IH, then we can write down here psi transpose K psi plus psi transpose, sorry, I times psi transpose H psi, right, and then this is again, as we said, it is diagonal. So, this is nothing but Kr, and this would be nothing but the modal stiffness of the corresponding undamped model, right, plus I. Now, this again would be diagonal, which is the matrix of damping coefficient, that is HR. So, now if you invoke the definition of structural damping matrix, the relationship between the structural damping matrix and modal loss factor, right, or the loss factor we define for the single degree of freedom system, right, then that we can apply now at the modal level, at the level of each mode, correct. So, for a single degree of freedom system, we just noted that the H is nothing but equal to eta times K, right. So, at the modal level, if we apply this relationship, that is for each mode we apply this relationship, then we can say that the structural damping coefficient for the Rth mode should be equal to the structural the modal loss factor for the Rth mode multiplied by the modal stiffness for the Rth mode. So, if that is so, then this matrix psi transpose K plus IH psi can be then written as Kr plus, so we can write this as Kr times eta R, right, which can be further written as Kr plus I, and we can write it as product of two diagonal matrices, that is Kr eta R. Okay, and we can in fact take the Kr common, which leads to a unity matrix plus I times eta R matrix, right. So, this is something we get, and now if we say that the eigenvectors, let us say they are mass normalized. Okay. So, if you we already have seen that how to do mass normalization. So, each eigenvector can be divided by square root of the corresponding modal mass, that basically gives us the mass normalized eigenvectors. So, let us say we have the phi as the mass normalized eigenvector matrix, mass normalized eigenvector matrix. So, if that is so, then now let us write down this relationship in terms of the using the mass normalized eigenvectors. So, we can write this as K plus IH phi. Now, the modal stiffness using the which is the modal stiffness of the corresponding undamped model, that would be nothing but the omega matrix of diagonal matrix of natural frequency square, that is the eigenvalues of the undamped model. So, we can write that matrix as omega r square I plus, so maybe I can put square bracket matrix I plus I eta r. So, that is nothing but the relationship, and the mass matrix phi transpose mass matrix phi would be nothing but simply a unity matrix, because now the eigenvectors are mass normalized. So, these are the basically now the expressions of orthogonality using the mass normalized eigenvectors, and here the omega r is nothing but the natural frequency, RF natural frequency of the undamped model. So, let us define what is called as modal model of this system. So, modal model of multi-degree of freedom system with proportional structural damping. So, this would then consist of natural frequencies, right, which are given by omega r, and these are nothing but the frequency of the natural frequency of the undamped model. Then we have the loss factors eta, right, and then we have the eigenvectors, which are nothing but the phi r, and this is nothing but the eigenvector of the corresponding undamped model. This is nothing but the eigenvector of the corresponding undamped model. Let me add word corresponding here also. And then all these quantities are defined for r is equal to 1, 2 up to n. So, there are n such natural frequency, loss factors and eigenvectors. So, these quantities together make up what is called as modal model of the system, right. Let us now consider the eigenvalue problem for systems with non-proportional damping. Which means that now the damping distribution is no longer proportional to either the mass matrix, stiffness matrix or a combination of the two. In situations where there are localized sources of energy dissipation, like for example, if there are joints, then the joints dissipate energy, and therefore, that basically may make the damping distribution non-proportional. So, that is one of the reasons for which the damping may be non-proportional. So, in this case now what is going to happen, that again we can solve the eigenvalue problem, does not change, and let us restate the eigenvalue problem, which is k plus k plus I h x naught is equal to lambda m x naught. So, the eigenvalue problem is still the same, looks same, but now the matrix H is non-proportional, and if we solve this eigenvalue problem, it again leads to eigenvalues matrix. So, let us represent the value of this eigenvalue matrix, right, and it is complex, as also was the case with proportional damping, and then we get the matrix of eigenvectors. This is eigenvector matrix, right, and these two again satisfy the eigenvectors satisfy the orthogonality. Okay. So, we still have the relationship psi transpose m psi is equal to mr and psi transpose k plus I h is equal to kr. So, these are still true, the orthogonality properties, right. So, these are the orthogonality properties. However, now one difference which occurs with case as compared to case of proportional damping is that the modes, the eigenvectors, they are now complex. They are now complex. So, that is the one difference that occurs as compared to case of the proportional damping case. Let us try to first understand what are what is mean by a complex mode and what does it represent. So, what is a complex mode? A mode shape being complex or eigenvector being complex. So, complex mode represents the situation where if you take any particular eigenvector, then any two elements of the eigenvector if you take, then the phase angle between those elements will be different than 0 degree or 180 degree, right, and this phase angle will be different for different choices of the two elements, right. So, therefore, in a complex mode the phase angle between any two elements is other than 0 degree or 180 degree, because 0 degree phase angle means they are in phase, 180 degree phase angle means they are completely out of phase, that is negative, basically one element is negative of other. However, in the complex mode this phase angle is different than 0 degree or 180 degree. So, therefore, it is not just question of algebraic sign, but there is a phase angle associated with each degree of freedom, and this phase angle is different for different different elements, right. The phase angle is different for different elements of the eigenvector. And what is the physical meaning of this mathematical structure? If we consider the vibration of the system in any particular mode which is complex, then it is seen that the different degrees of freedom do not undergo the vibration in a synchronous motion. The different degrees of freedom, they reach to their mean position and the extreme positions at different time instants, and therefore, it appears as if different points on the structure they are moving, they are traveling. So, if you look at the node which is defined as the location where the displacement is 0 in a mode, then that node would appear as if it is traveling, it is moving over the structure, because of the phase lag between the displacement at various degrees of freedom. Okay. So, therefore, here the various DOFs of the system reach to their mean and extreme positions at different time instants. Right. So, the motion of different degrees of freedom is not synchronized with respect to each other. Therefore, it gives the impression of a travelling wave moving over the system or structure, and this happens because the node positions of the mode are not stationary, they keep on changing their position. So, therefore, if you look at a complex mode, so let us take the example of a cantilever like this, and let us try to represent that what happens to the animation of the mode when the mode is complex and when the mode is real. So, if I also plot it for a real mode, right. So, if the mode is real, let us plot say the second mode shape of this cantilever beam, then this mode shape would be something like this, right, and when it goes to other extreme the mode would be like this, and at other time instants this mode will occupy this, the displacement will occupy this kind of deflection. Okay. So, what we see is that at the mean position and at other time instants the displacement at this point is 0, and this basically forms the node, right, of this particular mode, right. However, if we look at a complex mode, if the mode of this cantilever beam is complex due to non-proportional damping, then the plot of mode shape may look something like this. Okay. And when that mode the motion under this mode progresses, it may be like this and like this, something like this. So, what is happening is at different time instants the 0 displacement point is different, it is slightly moving. So, there is a shifting of the point at which the displacement is 0 and at different time instants, right, and that is why it appears as if this node is moving and gives the impression of a travelling wave. So, therefore, the modes are complex, and another implication is that now no longer the eigenvector matrix psi diagonalizes the stiffness matrix, right. So, no longer psi transpose k psi is diagonal, is not diagonal, right, which indicates that the modes we have got no longer basically they are same as the modes of the undamped model. Another of course obvious reason is that for an undamped system the modes are always real, but for a here the modes being complex they cannot be the modes of the undamped system. So, therefore, let us rewrite the orthogonality with respect to the stiffness matrix, and this is nothing but K R bar. However, we cannot write it now equal to a sum of diagonal matrix K R plus I times diagonal matrix H R, that cannot be done because this eigenvector matrix does not diagonalize not only the stiffness matrix, but it also does not diagonalize the damping matrix. If you use the mass normalized eigenvectors, right, let us say these are the mass normalized eigenvectors, then mass normalization can be done using the modal mass, and then we can write this as K plus I H phi, okay, and now this becomes a matrix of eigenvalues, right, it is a matrix of eigenvalues, and and this is a complex eigenvalue matrix because these eigenvalues are complex. Now, this complex eigenvalue matrix we can write as real part of the matrix plus the imaginary part, right. We can write that as real part and imaginary part, and if we call the real part of this matrix as diagonal matrix with diagonal values indicated by omega r dash square, then that basically represent the natural frequencies, right. And we can then break down the imaginary part, we can write that as a product of omega r dash square times say eta r, right. So, we should note that this complex eigenvalue matrix is diagonal, and hence these matrices, real matrices and imaginary part matrices, they are also diagonal. And what we have done is this, we have indicated the real the diagonal matrix by diagonal matrix having omega r dash square at its as the diagonal elements, and we have broken down the imaginary part into two parts, written as multiplication of two parts. One is the real part, which is the diagonal matrix of omega r dash square, and whatever is the remaining quantity, that we have called as diagonal matrix of eta r. So, eta r therefore the matrix that is left serves as the matrix of modal loss factors. Okay. So, now with this we can now define modal. So, model of multi-degree of freedom system with non-proportional damping. So, here now we will have eigenvalues, okay, or we can say natural frequencies rather. Because eigenvalues consist of natural frequencies and modal loss factors together, right. So, we can separate both these pieces of information and say that natural frequencies, they are nothing but omega r dash, okay, and then we have the modal loss factors, which is eta r, and then we have eigenvectors or mode shapes, which are psi r or phi r, the mass normalized eigenvectors, right. So, these of course are for r is equal to 1, 2 up to n. So, one thing has to be kept in mind that this omega r dash is different than omega r we got for the system with proportional damping, which is same as the natural frequency of the undamped model. So, that is different, and these eigenvectors are complex. Okay, so these eigenvectors are complex. So, for the model of the proportional system, let us check once that what did we write for the eigenvectors. Yeah, so here just yeah, so we have used the mass normalized eigenvectors, that is how it should be, right, the mass normalized eigenvectors making up the model. So, let us just wanted to confirm that, yeah. So, this is nothing but the model of the system with non-proportional damping. So, in this way we can see we have defined the eigenvalues, eigenvectors. Now, the next step is we would like to find the response of the system, the steady state response of the system to harmonic forces acting on the system, right. So, let us go to next page and let us find out the steady state response to harmonic forces. So, here now we are going to find only steady state response. As we said that time if we want to find the transient part of the response also, which is basically the complementary function, then that requires a solution of the differential equation in the time domain subjected to initial conditions, right, and that is something difficult for the system with proportional damping with structural damping, and hence we are only talking about the steady state part of the response, which is the response when the steady state has reached and the transient has decayed. And because the forces are harmonic, the steady state response would be at the frequency of the harmonic forces, and that is something we can analyze using the frequency domain model of the structural damping, right. So, let us do that. So, let us rewrite the equation of motion in the frequency domain, and that is minus omega square m x of omega plus k plus I h times x of omega is equal to f of omega. So, here the displacement and force, they are in the time domain, they are in the frequency domain at frequency omega. So, we can straight away write down x of omega as k plus I h, right. Now, k plus I h minus omega square m inverse times f of omega. And this matrix, as we have done even for the case of undamped systems, this can be represented by matrix alpha, which is the frequency response function matrix, times f of omega. So, therefore, frequency response function matrix is alpha omega is equal to inverse of the dynamic stiffness matrix. So, in this case the dynamic stiffness matrix is k plus I h minus omega square m inverse. And we also have said earlier that what is the reason for which this coefficient matrix should be representing the FRF matrix. The reason is that because this matrix relates the steady state response of the system to harmonic forces, right, and therefore, this matrix must be quantifying the relationship between the harmonic input and the harmonic output, and hence it represents the frequency response function matrix. Now, this matrix, it is equally true for both damping distributions, proportional as well as non-proportional. Okay. Here we have not made any assumption regarding the distribution of damping. It is this expression which is the relationship between the FRF matrix and the matrices K, M and H. This relationship is true for both the proportional and non-proportional damping distributions. So, this we can call as the direct method of analysis. So, let us write that, because here we are directly finding the solution from the differential equation. But now let us use the modal analysis method and see that how we can analyze the response. So, solution by modal analysis, as we have done for the undamped system also. So, here now we are going to first assume the damping to be proportional. Right, and now we perform modal transformation, which we have discussed in detail in the previous lecture. So, we perform modal transformation which is basically representing or expanding the displacement x of omega, right, in terms of the modes of the system, right. So, if you use the mass normalized eigenvector matrix, then the mass normalized eigenvector is phi, and let us say y omega is the matrix of participation factors, right. So, if you substitute this in the equation of motion and also pre-multiply that by phi transpose, then what is the resulting equation we get? Let us write that minus omega square phi transpose m phi y of omega plus phi transpose k plus I h phi y of omega phi transpose f of omega, right. So, this is something this is what we get, and now we invoke the orthogonality properties, and we know that due to orthogonality properties this matrix phi transpose m phi would be unity matrix, because we are using the mass normalized eigenvector matrix phi. So, this matrix is simply the unity matrix, and this is y of omega plus phi transpose k plus I h phi would be the matrix of eigenvalues, right. So, that matrix would be a diagonal matrix of eigenvalues like this. So, let me write omega lambda r y of omega, and phi transpose f omega we can write as f r omega, which is the vector of modal forces. So, let us write that as f r omega, right. So, so this is f r omega here is the vector of modal forces, right. So, now as we saw in case of undamped systems in the previous lecture, now this is again is an equation which is decoupled. These are decoupled sets of equations, right. These are decoupled equations, while the equations we wrote in the frequency domain using the k, h and m matrix, they were coupled equations. So, if I look at any particular equation, say Rth, so these are the n equations and they correspond to n modes of the system, each equation representing the vibration in that particular mode, right, and that equation is independent of the rest of the equations, and hence we can take one of such equations, right. And if we take, let us say, the Rth equation, if we look at the Rth equation, then that Rth equation is simply equal to minus omega square y r omega plus lambda r y of omega is equal to f r of omega, and therefore, the response y r omega, which is nothing but the modal response, which is also the can also be called as the Rth participation factor, then that becomes f r omega divided by lambda r minus omega square, and therefore, let me rewrite the modal response. Modal response in Rth mode is y r omega is equal to f r omega, okay, divided by lambda r minus omega square. And what was lambda r? And the lambda r for the proportional damping case was simply omega r square into bracket 1 plus I eta r. This is what we got, right, and hence y r omega can be written as f r omega upon omega r square into 1 plus I eta r minus omega square. And if you substitute the eigenvector, the Fr in terms of eigenvector, so rth eigenvector multiplied by the vector of steady state harmonic vector of harmonic forces, amplitude of harmonic forces, and therefore we get omega r square minus omega square plus I omega r square eta r. And therefore, now the response in physical coordinates we can find response in physical coordinates. This is the modal response we have got yr omega. Now we can obtain the physical response x omega is equal to, we can write this as sum of r varying from 1 to n, the eigenvector rth eigenvector multiplied by rth modal response, right. So, if we substitute this here, what we get is phi r transpose divided by omega r square minus omega square plus I omega r square eta r, and with r varying from 1 to n. And because f of omega is not dependent on the mode which is being considered, so we can just take it outside, it is a constant for a given excitation. So this is the you can see the expression we got for the steady state amplitude of the response at frequency omega, okay. And this depends on the eigenvalues and eigenvectors of the system. And you can see this looks pretty much similar to what we got for the undamped case, with some difference that now we have an additional term in the denominator represented by I omega r square eta r. So, that is the additional term that we have got. Now, let us find out for the non-proportional case. So, let us do it for the steady state response, right, by modal analysis for non-proportional damping case. Okay, once by modal analysis for non-proportional damping case. So, here we can proceed in the similar manner, only one difference would occur, right. So, so I would simply write down the expression directly, okay, because the all steps are similar and only the final expression would have some difference. So, it will be x naught, let me write. So, we get x of omega is equal to summation from r is equal to 1 to n phi r transpose divided by omega r. Now, omega r dash, now we are going to have omega r dash square, because these are no longer the same frequencies as the undamped modal natural frequencies, it is a different quantity, therefore, it is represented by omega r dash, right. So, omega r dash square minus omega square plus I omega r dash square eta r, and then we have f of omega. So, this is what we get for the system with non-proportional damping. So, the formula is in the same format, same form, except the difference that now the natural frequency omega r dash, it does not correspond to the natural frequency of the undamped model, plus the phi r, the eigenvector will be complex. Okay, that is going to be the difference. Let us define now, let us find out the FRF matrix from the based on the expressions we got. So, earlier we have defined FRF matrix, which gave us the expression or relationship between the FRF matrix and the spatial model of the system. The spatial model of the system consists of the mass matrix, stiffness matrix and the damping matrix. And we saw earlier that using the direct method, when we solved the response, we in the process defined FRF matrix, and it was basically the inverse of the K plus IH minus omega square M matrix. Okay. So, that was the relationship between the FRF matrix and the response and the spatial model. Now, we would like to find the FRF matrix in terms of the modal model, that is the eigenvalues and eigenvectors. So, let us write down the let us do it for the proportional case first. And if I write down the relationship for the proportional, for the case of proportional damping, then I have the relationship between the steady state response amplitude vector and a force vector given by phi r transpose divided by omega r square minus omega square plus I omega r square eta r f of omega with r varying from 1 to n. So, now to define, let us say if I am interested to find FRF alpha j k omega, right. So, alpha j k omega basically means that the response at the jth coordinate and the response amplitude at the jth coordinate divided by the force, harmonic force which is applied at the kth coordinate, the amplitude of the harmonic force applied at the kth coordinate, and with no force applied at the remaining degrees of freedom. So, effectively we have, therefore, this we can achieve by applying a unit harmonic force at say kth degree of freedom with no force at other degrees of freedom, right. So, this is kth degree. Okay. So, when that is done, what we get is x of omega, and when we multiply it to phi r transpose, we get phi r and then phi, now kth element of the rth vector divided by omega r square minus omega square plus I omega square eta r with r varying from 1 to n. And then if I am interested to know the displacement at only the jth coordinate, then we can obtain that from this vector simply as phi j r phi k r divided by omega r square minus omega square plus I omega square eta r with r varying from 1 to n. And this is nothing but the frequency response function alpha j k, because it represents the response, steady state response amplitude at j degree of freedom due to a unit harmonic force applied at only the k degree of freedom, and hence it is nothing but the alpha j k. And we can also write down the FRF matrix, because this is the relation we got for in terms of x of omega and f of omega vectors. So, the coefficient matrix must be nothing but the frequency response function matrix. So, therefore, the FRF matrix is simply alpha omega, alpha of omega. This is nothing but simply summation from r to n phi r transpose divided by omega r square minus omega square plus I omega r dash square eta. So, that is nothing but the FRF matrix, correct. So, you can see that on the right hand side we have the in the numerator phi vector phi r being multiplied to phi r transpose, correct. So, phi r has the dimension n by 1, right, while phi r transpose will have the dimension 1 by n, and that is how the product of the two would result into a n by n matrix, right. That is what we are supposed to have, because on the left hand side we have the FRF matrix which is also of the order n by n. Okay. Now, if we have the non-proportional case, then we can easily write down, for the non-proportional case we can simply write down the FRF matrix as, we have to just replace omega r with omega r dash and phi r would be complex, that is the only difference. Phi r transpose omega r dash square minus omega square omega r dash square into eta r. So, this is the FRF matrix for the non-proportional case. So, in this way today we have looked at the model analysis of multi-degree of freedom systems with damping. We defined eigenvalue problem, we then performed a steady state response analysis, first using the direct method and then using the modal analysis method, and we considered proportional damping as well as non-proportional damping distribution. So, I think we can stop here and we will meet in the next class. Thank you.